Okay, Unit 1, Objective 1, we are looking at domain and range, and then additionally at classifying a function as either one-to-one and or onto, and then in some cases classifying it as not a function. So we have some vocabulary terms here that we need to start by defining, making sure we're all on the same page. Domain's up first. Domain you would have first interacted with several years ago in math. A reminder that domain is the set of all x values for which a function is defined. Right? I'm going to skip domain very briefly here and skip down to range, which is the other one that you should have heard before. Range is the set of all y values. And then the second part is important because it's the distinction that we need to make between range and codomain. Range are the set of all y values that are produced from a function. And so an example of this is what I have written on my little post-it note here. If we have a function x squared, so our quadratic here, and I took an x value and plugged it in, that x value would then be part of my domain, so -1 would be part of my domain. And when I plug -1 into x squared, -1 squared, I get +1. And so 1 is a y value that is produced from a function, right? Produced by plugging in some part of my domain, whatever that result is part of my range, right? So domain, x values, range, y values that come from a function, which then brings us to codomain. There's a slight distinction here between codomain and range because codomain is also the set of all y values. However, it is the set of all y values that are possible. Every y value that could exist within a given situation, right? Range, therefore, becomes a subset of the codomain. Codomain is all the possible y values. Range are just those y values that are present from my function, right? So codomain, all of them. Range, just the ones that are part of my function. Okay, and then in a bit here we're going to review how we write how we write domain and range and that kind of thing. But really quickly, two more vocab words here. We have one-to-one and onto. And in our class, we are specifically going to be classifying whether a function is one-to-one or onto. And so kind of quick side reminder, function back in, it might have been Math 1 maybe, or Honors Math 8, I think, is when you learned the vertical line test, right? There can be no repeating x values. Or another way of saying it is that no x value can result in more than one y value, right? So that vertical line test needs to still be true. And that's what makes something a function. And maybe if you forgot that, you might want to write that off to the side here. Function, no x value can result in more than one y, or maybe you write function and then in parentheses vertical line test, something like that. Okay, but once we have determined that something is a function, we then are going to be classifying as either one-to-one or onto or both or neither, right? And so to start us off here, well, what does it mean to be one-to-one? Well, to be one-to-one, it's essentially exactly how it sounds. Right? Every x value will result in one y value. That's the definition of a function. Right? So if one x value has more than one y, it's not even a function, so we're not going to call it a one-to-one function. It's not a function to begin with. But in addition to every x value resulting in only one y value, to be a one-to-one function means that there is only one x value given any y value. Or another way to say that is no y value will go to more than one x. One-to-one. So there's no doubles anywhere. And again, you'll see what that looks like in a bit. But so one-to-one. Onto is a function for which each element of the codomain, right? And then backing up a bit, just a reminder, we're again still classifying it as an onto function. So if it's not a function, it's not an onto function. It's not a function to begin with, right? But if it is a function, then to be onto means that each element of the codomain, which are all the y values that are possible, have to map to at least one element of the domain. And it is important that we catch this, so if you have a highlighter or colored pencil or something like that, I would highlight or underline or something like that, that at least, because it is one of the differences between one-to-one and onto, right, is that an onto doesn't care if a y value goes to more than 1x, right? Doesn't care. As long as every element of the codomain maps to at least one element of the domain. So none of the codomain, which are all the possible y values, none of the codomain can get left out. Okay? Okay, I'm going to come back to this interval and inequality notation in a bit here. We're going to use that for the graph ones. But I want to take a look, or have us take a look at these vocab terms within the context of mappings, just so we have kind of a picture of what we're looking at. Okay? And so our directions here are going to be to identify the domain, codomain, and range. So we're going to start there. And then we're going to determine if a function is shown or not. If it's not a function, then we're going to stop there. If it is a function, we're also then going to state if the relation is one-to-one or onto, so that we can again hit each of those vocab terms that we have defined above. Okay? So let's go ahead and start with domain. Okay? So domain here. Within this particular mapping, our domain, again, all of your possible x values are going to be -1, 0, and 2. Each of those are my x values. When we're looking at mapping, we have our x that goes to our y. It is supposed to kind of illustrate this idea of plugging in an x and getting a y. Again, you should have looked at mappings back in Math 1 or Honors Math 8. So just kind of a quick reminder. So my domain here is -1, 0, and 2. Okay. My codomain, right? My codomain are all my y values that are possible, all of them on that other side. And so as I look on my range, I see 4, 6, 8, and 10. All of them are possible y values, and so all of them are part of my codomain, 4, 6, 8, and 10. Okay? My range then. Range are the y values that are actually produced from a function. They are the y values that are obtained by plugging in an x, by using one of my x values. And so as I look at these y values, notice that when I plug in -1, I get 8. When I plug in 0, I get 4. When I plug in 2, I get 10. The y values that are actually produced by the function depicted here are 4, 8, and 10. So 6, while it is a possible y value, part of my codomain, it never actually comes into being, so therefore is not part of my range. Okay? Next up we have, is it a function or not? Well, remember the definition of a function is that no x value can have more than one y value, right? I can't plug in -1 and get both 3 and 5. When I plug in -1, I should get one number, right? I can't plug in 0 and get -2 and 12. When I plug in 0, I should get one number from my function, right? I can't break the vertical line test. In this case, when I look at -1, if I plug in -1, I get one number, 8. When I plug in 0, I get one number, 4. When I plug in 2, I get one number, 10. Perfect. This is a function. And then the question then becomes, since it is a function, is it one-to-one? Is it onto? Is it both? Or is it neither? Okay? Well, so 1 to 1. What does it mean to be 1 to 1? 1 means that there is only one x value given any y value, right? Okay, well in this case, do any of my y's over here go to more than 1x? Well, 4 only results from 0. Right? 6 doesn't result anyway. It's not part of my range, right? So there's definitely not more than 1x that goes with my 6, right? There's nothing. 8, is there only one x value that goes with the 8? Yep. 10, is there only one that goes with the 10? Yep. And so this is 1 to 1. Another way to think of it is 1 to 1 means no duplicates, no duplicates, no double x's, no 2 arrows coming from x, no 2 arrows coming from y, right? 1, 2, 1, that's it, no doubles. Okay. Onto, what does it mean to be onto? Well, onto means it's a function for which each element of the codomain maps to at least one element of the domain. So onto doesn't care, again, about doubles, but it does care that every y value possible goes to an x. Has to. Every part of my codomain possible has to map to part of my domain. Okay, well, let's take a look at here. Does every element of my codomain, 4, 6, 8, and 10, do every single one of those numbers go to an x? Well, no. 6 doesn't. Right? And so this one is not onto, it is just 1 to 1. Okay, if there are questions on that, make a note of them. If you don't want to wait till the next day in class, then go ahead and email your teacher, but write them down now, right, so that you don't forget later on. We're going to go ahead and do another. If you feel like you got this down, well, maybe you pause the video and try this one on your own and see if you actually can do it on your own. If not, that's okay. Watch another one. We are going to practice these more in class, right? Okay. I'm going to go ahead and walk through it now, though. So same thing, domain, codomain, range. Is it a function 1 to 1 onto? Okay, so domain, all my x values. So what are my x values here? My x values are 3, 4, 5, and 7. Okay, codomain. Codomain, all y values that are possible. What are my possible y values? We have 5, 8, and 9. Okay, range, all y values that are produced. Okay, so which one of these y values actually come from an x? Well, 5 comes from both 3 and 5. 8 comes from 4. 9 comes from 7. And so in this case, my range, the y values that are actually produced are 5, 8, and 9. This is an instance where my codomain and my range happen to be the same. Okay, next, is it a function? Remember, a function, no repeating x's, right? I can't have any x that results in more than one y. Well, 3, does it result in more than one y? Nope, it just goes to 5. 4, does it result in more than one y? Nope, just goes to 8. 5 more than 1? Nope, just to 5. 7 more than 1? Nope, just to 9. And so this is a function. And then is it 1 to, a 1 to 1, onto, neither, or both? Okay, well, 1 to 1 first, exactly like it sounds. There should be no doubles, right? Or triples for that matter either. No doubles, no triples. Every y value should just have one x value. There should be only one x value given any y value. Well, 5, is there only one x value for this 5 that we were given? No. This 5 comes from both 3 and 5. And so this one is not 1 to 1, right? There's a double here. 8's fine. 8 only comes from 4. 9's 5. 9 only comes from 7. But 5 is our issue here. And then finally, onto. Onto, every element of the codomain has to map to at least one element of the domain. Well, my codomain is 5, 8, and 9. Does every element of that codomain map to at least one element of my domain? Well, 5 5 definitely goes to at least one element. It goes to 2. Remember, onto doesn't care about doubles. Onto is just, does every y go to at least one x? Right, every possible y go to at least one x. Well, 5 goes to 2 of them, 8 goes to 1, 9 goes to 1. So yeah, every element of my codomain goes to at least one element of my domain, and so this is onto. Okay. Coming back up here, we now want to look at this graphically as well, and so a couple of notes for graphically. In this class, we are going to look at both interval notation and inequality notation. I will say this, headed forward, I know most of you will probably end up in either Calc AB or Calc BC next year. And just so you know, within calculus, we pretty much use interval notation only, but you do need to be able to use inequality notation. Sometimes you will have problems written in that form, and so we need to be able to very comfortably read it. And so we are, like I said, in this class, especially here at the beginning, going to use both. Eventually we will start to kind of just have you do one or the other, or give you a choice as to which one you prefer. But here up front, again, we're writing in both. Okay, so first up, interval notation, which like I said will be headed forward, probably the most common one you use. Interval notation, we use square brackets. So square brackets, talking like this. Square brackets, when you want to include an endpoint. If you put a square bracket on your interval, say there's a -3 next to that square bracket, you're saying there is a point at -3. -3 is included. We use parentheses when you do not want to include an endpoint. So if you put a parenthesis next to the -3, you're saying there's a hole, which is an open circle, just as a reminder on your graph. An open circle is a hole, and you're saying there's a hole at -3 as opposed to a point. Again, a point would be a square bracket, a hole would be a parenthesis. And then it is important here, I would again highlight or underline or something this note here. We always use parentheses on infinity and negative infinity because you can't put a point at infinity. We can't reach it, right? Buzz Lightyear's statement of to infinity and beyond is not possible, right? You can't reach infinity, and so you can't put a point at infinity. And so we have to put a parenthesis because there will never be a point at infinity or negative infinity, right? When you're writing your intervals, your smaller number will always go before your larger number. And then we use this U, by the way, if you want to give this a name, is called union. So again, if you were to be reading an interval aloud and you saw that U, you wouldn't just say U, you'd say union. But we use a union symbol to connect intervals when there's more than one interval for the domain or the range. And again, you'll see what this looks like in a bit. Okay, for inequality notation, we use equal when you want to include an endpoint. So equal says there is a point there. So endpoint is kind of like square bracket. I'm sorry, let me say that differently. Equal, so like greater than or equal to this guy here, or less than or equal to. Okay, that is kind of like a square bracket. We don't use the equal when we don't want to use the endpoint. So just a less than or just a greater than would be like an open parenthesis, right? Again, we never use equal for plus or minus parenthesis. You can't, I'm sorry, for plus or minus infinity, you can't put a point at plus or minus infinity, so you can't use the equals. Okay, we use our inequality sentence, and then we use or as opposed to the union symbol for intervals. Or is for your inequality notation to connect intervals when there is more than one sentence for the domain and range. Okay? And so let's look at these with our graphs here. We're still going to do the same thing we did with the mappings, with identifying domain, codomain, range, classifying as function, classifying as one-to-one or onto. Okay? So for these first two, we're just going to do the inequality notation. I like to start with inequality notation because I find students are usually most comfortable with this one. Okay. So let's go ahead and start with our domain. Okay, so domain on a graph. So domain are all of the possible x values that are part of your function, right, for which a function is defined. And so when you're looking at identifying a domain, you're starting on the left side of the graph over here, right, pretending that we're headed out to negative infinity, and you're asking yourself, at what point on the left does my function start, right? At what x coordinate do I first have part of my graph? And in this case, this graph, if you notice, it has an arrow here which says that this graph is going this way forevermore, right? Meaning that this graph here starts at negative infinity, which I know is kind of a funny thing to say because you can't start at negative infinity if you can't reach it, right? But it's a representation of that fact that that graph goes forevermore left. So it quote unquote starts at negative infinity. Okay? Now we're using inequality notation, so we're going to be talking about less thans, greater thans, less than or equals, greater than or equals, that kind of thing, right? And so in this case, negative infinity, remember, we never use equal for negative infinity. We can't reach negative infinity, so we're just going to do less than. And then domain are my x values, right? And then starting on that left, you're going to work your way going towards the right, because x values are left and right, just like the x-axis. So you're going to work your way right and go, is there at any point that I reach a value of x and I see a hole with no corresponding point, or an asymptote, a vertical asymptote, I should say, right? So again, some place where there is no point, or does my graph stop altogether? And so I'm going to work my way right here, and again, this line or this arrow shows this graph keeps going. So at negative, whatever this is, 1, 2, 3, 4, 5, 6, 7, at negative 7, yeah, there's a point. I mean, I don't know what it is, but this graph keeps going, right? So there's a point somewhere down here. And at negative 6, there would be a point. Again, that graph keeps going. Negative 5, there's a point. Negative 4, there's a point. Negative 3. Negative 2, there's a point. Negative 1, there's a point. And they actually help me out, and they even tell me what that point is. 0, there's a point. 1, there's a point. It's right here, whatever that is. 2, there's a point. It's a 3. And then again, there's an arrow. And so that graph is going to keep going, right, forevermore. 3, there would be a point somewhere probably pretty high up here. This graph is increasing pretty steeply. 4, therefore, would have a point really high up here. 5 would have a point even higher. 6, even higher. 7, higher still, right? But like there keep being points for all of these x values. So this graph keeps going all the way to infinity. There's never any break. And again, negative infinity and infinity, we never use equal. And so that's how I write my domain. Okay? Codomain. Codomain, ladies and gentlemen, is probably going to be the easiest one to write on graphs. And so just so you know, we're not really intending to ask you to write it on your homework, because for a graph, the codomain is always exactly the same. Codomain are all of the possible y values, not just the ones that come from the function, but literally every possible y value. Well, on a graph, every possible y value is negative infinity to infinity, right? I think of it this way. I could graph a point at y equals negative 2,000, right? In this graph, as we're going to see in a bit, we don't have a point at y equals negative 2,000. But I could draw one there if I extended the graph negative 2,000 downwards, right? So codomain is every possible y, meaning on the graph, codomain is always negative infinity to infinity. And we're going to put y here because it's all the possible y values. And so that's going to be my answer for all of them. Again, remember, negative infinity to infinity never equals. Range then. Now range are only the y values that actually come from my function. And so in the same way that with domain, we started on the left and worked our way right, looking for any holes or asymptotes or lack of points, with range, I'm going to start all the way at the bottom and I'm going to work my way up, looking for any holes or asymptotes, that kind of thing. And I'm going to start with my starting point. Where's the first place that I see something on my y-axis, or I should say in relation to my y-axis? Well, this little dotted line here before, for those who haven't seen it, it's called an asymptote. This function is getting funneled alongside this asymptote, meaning that it won't ever cross that horizontal asymptote, right? That means that down here at -7, there will never be a point at y equals -7. This graph comes alongside the line but won't ever cross over it. There's no point at -7. So I'm actually not going to start at -infinity for this one. I don't go down all the way. I'm not even going to start at -7. I'm not going to start at -6. In this one, I'm going to start at -5. But notice, is there a point, or will there be a point ever, for y equals -5? Well, no. This line, this graph, is going to come alongside that asymptote but never touch it. Because there is no point, I'm not going to use an equals. I will only ever use an equals or a square bracket when we get to interval notation. I will only ever use an equals when there is a point. Okay? And then I'm going to work my way up. Okay, so I start at -5. There's not a point, but that's where I'm starting. Is there one at -4? Yep. -3, -2, yep. -1, yeah. 0, 1, 2, 3, 4, 5, 6, 7, 8. There's an arrow pointing my way upwards, so I'm going to keep going. Every y value up here will have a point on the graph. And so I'm going all the way to infinity. And remember, infinity is never, ever equal. Okay, and then function, 1-to-1 or onto. Function, again, vertical line test. No x value can result in a corresponding y value. And so if I were to drop vertical lines through this graph, the question would be, is there any place where when I drop, if I were to draw a vertical line in, let me go ahead and do that with highlighter here just so you can see what I'm talking about. If I were to draw a vertical line in anywhere on that graph, is there a place where I can draw a vertical line in and hit my line, or in this case my curve, more than one time, indicating that one x value has more than one y value that goes with it? Are there 2 points on that vertical line? Well, no. Nowhere that I draw that line will I have more than one y value, more than 1 point. So this one is a function. Yay. And then, is it 1-to-1? Is it onto? Is it neither? Is it both? Okay. Well, in this case, 1-to-1 first, right? Every y value needs to correspond to only one x value. Some people like to call this the horizontal line test, just because they like that match with the vertical line test function, horizontal line test 1-to-1. But that it is that kind of same question as the vertical, so I'll do this with a pink highlighter. Is there any place where I have a y value that corresponds to more than one x? Because I can't have that in a 1-to-1 function. 1-to-1. So is there anywhere on this graph where I can draw in a horizontal line and hit more than 1 point? Well, yeah, no matter where I draw this line in, I won't ever hit more than 1 point. And so this one is 1-to-1. And then last but not least, does every element of my codomain, remember codomain on graphs are easy, it's everything, -infinity to infinity. Does every element of my codomain map to at least one element of my domain? Another way of saying this would be, because codomain is always going to be -infinity to infinity on a graph here, is my range -infinity to infinity? If my range isn't -infinity to infinity, then that means that some y values, some parts of my codomain were left out. Every part of your codomain has to be there. has to map to part of your domain. If there's any y values left out, like the 6 over here, then it's not 1 to 1. Well, yeah, there were a bunch of y values that were left out on this graph. There was nothing at -6, nothing at -7, nothing at -8, aka my range was not -infinity to infinity. And so because I have some y values that were left out of my codomain, this is not onto. Okay? Okay, if you feel like you got it just from that one, go ahead and pause the video, give the next one a shot. Remember, we're going to keep practicing it in class. Domain. Okay, domain. So starting on the left, working our way right. What is my smallest x value? The furthest left I go. And then as I work my way right, are there any holes, asymptotes? Where do I stop? Okay. As I look on this graph, as I'm out here at x equals -infinity, this arrow is pointing forever more left. And so I'm starting at -infinity. And remember, -infinity will never be equal. Okay? And then you're going to work your way right, looking for places where I don't have a point at an x value, a hole, an asymptote, etc. Okay, well, at -7, yeah, I've got a point somewhere up here, wherever that arrow intersects. -6, yeah, -5, I've got something. -4 is a little bit down. -3 is down here at like -3-ish. But -2, look at it, x equals -2. There is no point anywhere on my graph, no point. Okay? And so -2, I actually have to break at -2. I can't skip over -2. Okay, I have to break there. There is no point at -2, and so I'm going to write just less than. If there was a point, I would say -2 is less than or equal. Actually, it'd be -2 is greater than or equal to. But because there's no point at -2 at all, I'm going to put just less than. Remember, when there is more than one interval, we're going to write or, and then write our next statement. So the question then becomes, well, I went from -infinity to -2. Where did my graph pick back up again? Well, my graph picked back up again at -2. Right? I went to -2, hole, started right back up again. So I'm going to start at -2. Again, there is no point, so no equals. And I'm going to work my way over. There's something at -1, something at 0, something at 1, something at 2, something at 3, something at 4. Uh-oh, there's a hole at 5 once more. And again, no equals. If there was another interval, I'd write or and write the next interval, but this graph never picks back up again. The graph is done at 5, and so that's the end of my domain. Okay? Codomain, again, every possible y value. That's handy for graphs. It's always -infinity to infinity. I could write something at all of those points. Range then is, where do I actually have a point? Well, range, okay, on your graph here, go all the way down to the bottom, okay, and then work your way up. What is the smallest y, the furthest down my graph goes? Well, in this case, my graph, there's no arrow pointing my way downwards, right? So my graph doesn't go down to -infinity. My graph doesn't start till right here at -5, at y equals -5, right? That's the first place that I see something of my graph. Now it's a hole, so no equals. And I'm going to work my way up looking for a lack of point. Well, there's something at -4, something at -3, something at -2. -1, sometimes people want to say there's no point at -1 because they're looking at this hole over here. But there actually are points at y equals -1, right? This point is at y equals -1. So are all of these. These are all at y equals -1. This one over here is at y equals -1. So I do have points at -1, at y equals -1. Right? I've got a point at y equals 0, point at 1, 2, 3. This arrow's going up, so I'm going to have it all the way up to infinity. And again, one more time, infinity and -infinity are never equal. Okay? Is it a function? Vertical line test. Is there any one x that corresponds to more than one y? Can I ever drop a vertical line through my function anywhere on that function? Doesn't matter where. Anywhere on that function. Can I drop a vertical line and hit more than one point? I can't, no matter where I put it. So this is a function. Is it 1 to 1 or onto? Okay, 1 to 1, right, is what it sounds like. Is there anywhere where I could draw in a horizontal line and hit more than 1 point? Well, yeah, there's quite a few places, right? Even this one line I already drew hit the graph here and here, right? Meaning that I have one y value, whatever that is, that's like negative 3.2 or something like that, one y value that has more than one x. If I were to draw it with arrows, that negative 3.2 would go to multiple x values. And so this one is not 1 to 1. Okay, is it onto? Remember, onto every possible part of my codomain, which is always negative infinity to infinity for graphs. Every part of my codomain has to have a point. It has to go to the domain. Okay, well, that is not true. There's a bunch of places that don't have points. Y equals negative 7 doesn't have a point. Y equals negative 5 didn't have a point, right? There was no equals there, right? So there's lots of places. So this is neither 1 to 1 nor onto. Okay. Okay, we've got two more. Interval notation is exactly the same as inequality notation. It's just that instead of writing your less thans or greater thans in the x, you're going to use parentheses. Instead of writing the equal to's when there is an equal to, which actually this one didn't have any equal to's, so I won't be able to show that, but when there was an equal to, you would write a bracket. Okay? So same thing, if you feel like you want to give it a go on your own, you can pause the video. If you'd like to watch through one and maybe try the next one, you can do that as well. Or if you need to watch two, that's fine. Again, we are going to practice it more in class. Okay? So domain. Again, all the way left, what's the furthest point you see? Well, in this case, there's no arrow, right, pointing me left. I'm not starting at negative infinity for my x values here. I don't have anything at x equals negative 7. I don't have any point at x equals negative 6. The first place that I see part of my graph is at x equals negative 5. And then, question, is there a point? Because if there is a point at negative 5 where I'm starting, I'm going to put a square bracket. If there's no point, then I'm going to put a parenthesis. Well, what happens at x equals negative 5? Is there ever a point on this graph at x equals negative 5? Nope, just a hole, so this is a parenthesis. Remember, it's always smaller number than larger number. So I'm going to go ahead and put a parenthesis, and I'm going to work my way over, looking for any spots where I don't have points at those x values. So I've got something at negative 4, I've got something at negative 3. Okay, negative 2 again is a place where some students might want to stop. They see that hole and they go, there's no point there, and so I have to stop at negative 2, but there actually is a point at x equals negative 2. Look a little bit higher. There's a point up here at x equals negative 2, and so I'm going to keep going. Okay, x equals negative 1, I've got points. Negative 1/2, I've got a point. Negative 1/4, I've got a point. 0, 1, I've got a point. And then, look right here, there's a break in the graph. Everywhere between x equals 1 and x equals 2, there is no point there, right? There's nothing at x equals 1.5, no coordinate point there. And so my graph actually stops momentarily at x equals 1. And so that's going to be the end of my interval. I'm going to go from negative 5 to 1. The question is, do I do a bracket or do I do a parenthesis? Well, to answer that, again, I use a bracket when there is a point, including the point. I use a parenthesis when you don't include the point. So is there a point at x equals 1? Yes, there is. It's right there. And so I'm going to use a bracket. Okay? Now, if my graph stopped at that point, I would stop. But there is another portion of my graph here, and so again, for intervals, you use a union. Okay, so I'm going to put a union here. And then where does my graph start up again? Well, it doesn't start up again right at 1. Again, there's a break in the graph here. This graph doesn't start up again until x equals 2. Same question, parenthesis or bracket. Is there no hole, or is there no point, or is there a point? There is no point anywhere on this graph at x equals 2, so I'm going to do a parenthesis. And then this graph keeps going, x equals 3, x equals 4, x equals 5, x equals 6, and the graph stops there. Is there a point? Yes, there is, and so we're going to do a bracket. Okay. Codomain, again, codomain, easiest thing to answer on a graph. It's negative infinity to infinity. Again, on an interval notation, just like with inequalities, we never use equals. With an interval, we always use parentheses. There will never be actually a point at negative infinity or infinity. Range, what y values are there actually? Okay, so starting low, what's the lowest y value you see? Well, we have no negative infinity because there's no arrow pointing downwards, right? So I'm not starting at negative infinity. The lowest place on the graph that I see is here at negative 7. Is there a point or not? Well, at y equals negative 7, there's never a point, so that's a parenthesis. Working my way up, I've got something at negative 6, negative 5.5, negative 5, negative 4, negative 3, and then, uh-oh, there's a break again. There is nothing at negative 2.5 or negative 2 or negative 1.5. My y values stop momentarily at negative 3. Is there a point at y equals negative 3? There is. It's out here, and so that's a bracket. Union, because there's going to be another interval. Where does my graph start back up again? Well, again, there's a complete break in the graph, so it doesn't start back up again until here at y equals negative 1. Is there a point? Yes, there is. So it's a bracket. And then working our way up, we have something at 0, something at 1. Again, 2, potentially people might want to say there isn't, but there is. There's a point at y equals 2. It's right there. Y equals 3, there's a point. Y equals 4, y equals 5, y equals 6. And then because there's no upward arrow, we aren't going all the way to infinity. My graph stops at y equals 6. Is there a point? Yes, there is. And so it's a bracket. Okay, function. Is it a function? Okay, vertical line test. Is there anywhere I can drop a vertical line and hit more than one point? Well, yes, there is. Look at negative 1, or x equals negative 1.5. At x equals negative 1.5, when I drop my vertical line through there, I do have more than one y value. X equals negative 1.5 results in a y of about 1.5 and another y of about 1, 2, 3, 4-ish, right? So there is a repeating x. This means this is not a function, which means we are not going to classify it as either one-to-one or onto, because both one-to-one and onto in our class are going to require it to first and foremost be a function. Function, right? If it's not a function, we're not going to classify it. Okay, last one. Go ahead and pause it if you'd like to. Restart it if you want to check your answers or watch through it. We'll practice more in class. Domain. What's the furthest left we go? Well, there's an arrow pointing that way. So, furthest left we go is negative infinity. There is no point. There will never be a point at negative infinity or infinity. Okay, working our way right, we have something at negative 7, negative 6, negative 5, negative 4, negative 3, uh-oh, negative 2. There is a hole. Nowhere on my graph do I have anything at x equals negative 2. There is no point, so it's a parenthesis. Union, because there's more to my graph. It picks right back up again at negative 2. Again, there still is no point, so we are still doing a parenthesis. And from negative 2, we have something negative 1, 0, 1, 2, 3, 4, 5, 6. We see an arrow. It's going to keep going all the way to infinity. Okay? Codomain, easiest one. Always negative infinity to infinity on a graph. Range. Okay, my range. Furthest down I go, well, there's an arrow. It's pointing me downwards, meaning this graph's going to keep going. The lowest y that I hit well, I can't actually hit it, but is negative infinity, right? Remember, never actually a point, so always a parenthesis, never an equal. And then working my way up. Okay, this graph is a little deceptive. When we're sitting here at y equals -5, it's tempting to want to say, oh, there's a hole, there's no point. But there is a point. What on this graph shows me that I actually do have a point at y equals -5? It's that arrow. That arrow's showing that I'm going to keep going down, right? At some point, however this keeps going down, I will cross y equals -5. There will be a point there. So I do have a point at y equals -5. -4, -3, -2, -1. I've got points all the way up. There's an arrow pointing me upwards, meaning this is going all the way to infinity. Is it a function? Okay, is there anywhere where I can drop a vertical line and hit more than one point? Well, no. Nowhere on that graph will I hit more than one point, so this is a function. Is it one-to-one or onto? Well, one-to-one, is there anywhere where I can draw a horizontal line and hit more than one point? Because again, I can only have one. Well, yeah, there's a lot of places where I can hit multiple points, right? All of these horizontal lines hit multiple places on my graph. I have multiple points, and so this y value here at y equals 1 has 3 x values that it goes to. If I were to draw that as a map, x equals 1 would have 3 arrows coming from it. That is not one-to-one. Okay? And then last but not least, is it onto? Does every part of my codomain, negative infinity to infinity, have a point? Well, yeah. There's no y value, right? You can see that in my range. My range maps to my matches my codomain. Negative infinity to infinity is my range, meaning that every y value that exists has a point at it. And so that is onto. Every possible part of my codomain, negative infinity to infinity, does exist on my graph. There is a point at all of those y values, and so it is onto. Okay? Okay, that's 1.1.